So, today we got trends, ionization energy, radius, things like that. We're going to go a little bit deeper into some of this stuff. Now, in your notes, it has you do ionization energy first. I'm going to start with atomic radius because I think atomic radius is the best way to explain ionization energy. So, we're going to start with radius. You should recall or remember the trend, at least for radius. Maybe not completely understand the why, but you should at least remember the trend. Okay, so if you recall, how does the trends work? Can you tell me that without looking at your notes? Anybody?
Isn't that one the largest one?
Yep, largest to smallest. Okay, so from top to bottom, you get large. Can you explain that? You should be able to explain that one pretty easily. That one's the easy one to explain.
Because the protons have a stronger pull because...
Top to bottom?
It has to do with electronegativity.
Because like, well those ones, wait,
Why do I go from top to bottom? Why does it get bigger?
because there's more electrons and more energy.
More energy levels. Okay, yes, you do have more protons, but that last electron, or the one electron that each of these guys have here, or this guy has, okay, is going to be in its furthest energy level away from the nucleus. So we know that as you add energy levels, you're one, giving electrons more energy so they can spend time further away from the nucleus. Okay? Those electrons, I kind of stated both of them at the same time. They have more energy and thus are farther away from the nucleus. The farther away from the nucleus you are, the bigger your radius. So I suppose I should probably define radius here. There's your nucleus. Your radius would be like you would expect from your outer energy level electron to your nucleus. I'm sure you guys assumed that already, but just in case. Right? So from top to bottom, that one's pretty easy because you're adding an energy level as you go down. Okay? Left to right's a little bit trickier. As I go from left to right, it's a little bit tricky because we stay within the same what? Energy levels. Okay? So top to bottom's easy because we're adding energy levels. We're getting further away from the nucleus. Pretty common sense, I think, on that. But going left to right, we're staying in the same energy level. And the trend actually is, as I go from left to right, is it gets smaller. Right? In the idea of why it would get smaller, I think this is what you were about to say for the top to bottom. Right? You remember it all?
Addition of a proton pulls them in more than the addition of electrons pushed out.
I'm actually impressed that you remember that, Rylan.
Yeah.
Okay? What happens here is, as we go from left to right, we're staying within the same energy level, so we're not really getting further away from the nucleus much. Okay? But as I go from left to right, we're adding protons as well. So yes, we're adding electrons, but we're also adding protons. And for whatever reason, you got to think about electrons being able to repel and shield other electrons away from the nucleus, and then the additional protons in the nucleus pulling electrons towards itself. Okay? So let's just say there's our first, there's our second. So there's my two electrons here. Okay? As I add an electron outside, I'm also adding another proton. So I got my 3 protons. Okay? Adding another electron, adding another proton. Notice they're kind of staying within the same energy level. These electrons are going to start shielding these out, but these aren't really going to shield each other out too much. Add another proton. So we're really adding electrons to the same energy level. And as we do that, those protons that are being added are twice as effective in pulling the electrons inward, making the radius smaller, as the electrons are in repelling and shielding each other away from the nucleus. Okay? Now it gets a little bit goofier when we talk about ionization energy and how, well, I'll wait till we get to ionization energy. to talk about that. Okay? So the thing you gotta remember is as you go left to right across the periodic table, yes, I'm adding electrons, so in your head you might be thinking, shouldn't they be getting further away from each other? But you're also adding protons. And protons are twice as effective at pulling in as electrons are at shielding other electrons away, or repelling other electrons away, making it bigger. Right? Is that?
Fluorine.
Is what?
Is that fluorine then?
Which one? Oh, I don't know. I was just throwing electrons in there. What do you got?
1, 2, 3, 4, 5. Yeah, that's fluorine.
Okay. But the smallest is going to be neon in that group. Okay? Now let's go back to ionization energy. So we're going to probably camp most of our time here. Alright? So if you remember, ionization energy is this idea of how much energy would it take to remove an outer electron. Okay? So, sometimes it takes more energy to remove, and other times it doesn't take as much energy. And the number one factor that causes this, I think, is radius. Okay? If you've got a radius like this versus a radius like this. There's an electron here, an electron here, here's your nucleus. Which electron is going to be easier to remove?
One on the right.
Why?
It's further away.
It's further away, has more energy already, doesn't require a lot of energy to remove that electron. Okay? So, the trend for ionization energy should be opposite that of radius. So as I increase in radius, I should be decreasing in ionization energy. This electron should be the furthest away of any other atom's electron. It's so easily removed that it's very reactive. Absolutely. Yep. Right? Now, this is also reactive, but for the opposite reason. It so easily gains an electron. Is that mine or?
Yeah.
Oh, you're asking to borrow. Yeah, that's fine. Okay? So as radius gets bigger, it's easier to remove an electron. As radius gets smaller, your electrons get close to the positively charged nucleus in the center, and so therefore it's much more difficult to remove and takes more energy to do so. Okay? So I think it's easiest to kind of think of ionization energy based on radius. That's why I talked about radius first. Okay, so here's your trend, opposite that of radius. Okay, so first ionization energy would be removing the first electron. Second ionization energy will be removing the second electron. It always takes more energy to remove the second electron than it does the first. Why?
Because it's charged.
Closer to the positive charge.
Both. Because it has a positive charge, and because it has a positive charge, it's also closer to the nucleus. So for example, let's say, let's go back to fluorine here. I think this was fluorine. So I got 9 electrons and 9 protons for a fluorine atom. Okay? If I remove an electron from fluorine, this is going to make me have 8 electrons and 9 protons, so fluorine would have a positive charge, correct? Okay? So I remove my first. That would have been the first ionization energy. Removing my second electron is now removing it from something that has a positive charge. So essentially now the 9 protons is probably pulling the 8 electrons a little bit tighter, making the radius a little bit smaller, and thus making the second electron a little bit more difficult to remove. Does that make sense? So then let's say I take another electron. Now I've got 7 electrons, and I have a 2+ charge. Now the third ionization energy is going to be even more difficult, or more energy needed to remove it, because now I have 2+ charge, and so forth. I can continue going and going and going. Now, everybody open up your books. Turn to page 319. There's a couple graphs here that I want to show you. ACT 101 here. Let's analyze the graph. 319. Let's look at the table first. Table at the top of 319. Okay? So if you look there, it appears that those are the elements in period 3. So starting with sodium, going all the way over to argon, period 3 elements. Okay? At the top it says I1, I2, I3, I4, I5, I6, I7, and so forth. What do you think those I's mean?
The iron.
Okay. So let's stick with I1, because the trend makes sense. As you go from sodium down to argon, ionization energy gets larger. Does that agree with what we've been talking about? Why is argon's ionization energy so much higher than sodium's? It's to the right, so it has the smallest radius, so therefore its electrons are going to be a lot closer to the nucleus, therefore it's going to be more difficult to remove and take more energy to do it.
For sodium, it jumps.
Okay? Okay? And now, as you go to the second ionization energy, what you should notice there is sodium has an absolutely astronomical amount of energy that it jumps to. Versus magnesium on down still follows the trend. Everybody see it? The question is, why does sodium have such a huge jump when everything else's trend kind of stays the same?
It's changing energy levels.
Look up here. How many valence electrons does sodium have?
One.
We have one valence electron that sodium has. So that ACT really zapped your mental capacity. It has one. Okay, so if the first ionization energy is removing that first one, then what is the next electron really I'm removing?
From the second energy level.
Okay, what kind of electron? What's the name of that? It's got a name. We have valence electrons and we have, what is it called? It's got a name. It was in this chapter.
Interior.
Look on the table. It says it. Core electrons. Absolutely. I said valence electrons are the outer energy level electrons, and core electrons are everything else. I promise it's in there. Let's find it.
I believe you.
Where is it?
Here?
Right there. You even highlighted it. What was that?
I don't worry about vocab for that for the test.
Okay, so core electrons are anything that aren't the valence electrons. And the reason why core electrons are more difficult to remove is now so it's imagine sodium all of a sudden turning into removing an electron from neon. More difficult to remove an electron from a full outer energy level and the second energy level than it is to remove one valence electron from an energy level above. And you can kind of see this trend. Let's look at magnesium. Magnesium has 2 valence electrons, so it would be the third electron where you'd be removing a core. In aluminum, it would be the 4th electron where you'd be removing the core. And so forth. Are you seeing where the jump is?
It starts happening.
Okay? Otherwise, up to that point, doesn't it appear that the argon's ionization energy is always higher than the ones below it, or the ones to the left of it? Assuming you're not removing a core electron. Okay? And that would follow the idea of, as it becomes more positively charged, it becomes more difficult to remove because your radius gets smaller ever so slightly. Okay? So, things to remember. Radius, top to bottom, gets bigger. Left to right, gets smaller. And the reason why it gets smaller left to right is because protons are twice as effective pulling towards as electrons are in shielding. Okay? Ionization energy. The first ionization energy is always going to be the smallest. And second's going to get bigger, third's going to get even bigger, fourth's going to get even bigger. Because of why? Why does the ionization get bigger? Removing the second, third, fourth, and fifth. What was that? Because it becomes more positively charged, thus making the radius a little bit smaller and more difficult to remove. And then the core electrons, you see the biggest jump, because there you're dropping an energy level and you're getting your radius is getting much smaller really quickly. Because you're completely losing a whole energy level.
What if the ionization energy be smaller, like once you go from francium to the last ionization?
Francia?
Or not, no.
Fluorine?
Or like, yeah, so you take away like the first,
So then the second it'd be higher energy.
but so it gets higher and higher and higher, but wouldn't it get lower when like it only needs one?
It only needs one.
One, or like it needs one to be taken away and it is.
Well, you gotta remember, as I'm removing, so say I remove 6 electrons. Okay, I've only got 3 electrons remaining, and I've got 9 protons in the nucleus. So like, those protons are pulling on the electrons 3 times as much as they would pull on an electron if it had 9. Does that make sense? So that would make its radius real small and very difficult to remove. Now that probably isn't gonna ever happen, because it's just not going to give up that many electrons. I mean, I suppose they could forcibly do it. And if you look on here, although this isn't fluorine, but let's say chlorine. Okay, removing its 7th electron takes 11,000. Is that joules of energy? It doesn't say that. It doesn't say what. It doesn't appear to say what the unit is. I'm guessing it's joules of energy. Okay. So yeah, you got to think about the fact that you've got a whole bunch of protons that aren't changing, and that's why it's going to take a lot more energy. Okay. I think anything else? I think that's it. Oh, actually, graph on the bottom. Look at the graph on the bottom. So you can see for each period the energy level graph. Let's just look at period 2, period 3, and so forth. Okay. Starting with lithium. Everyone see lithium there at the bottom. Bottom left corner. Everyone there? You don't have your book. Roger your book open. Holy cow. What? That's not, wow, that is the right page. Okay, look at lithium. Okay, ionization energy gets bigger when you go to beryllium. Makes sense, right? Then what do you notice? Takes a little dip. Then it follows the trend. Then at nitrogen to oxygen takes a little dip again. Okay, the reason why it takes a little dip has to do with your orbitals. The boron happens after your beryllium S sublevel is full. Okay, so follows the correct trend. This is easier to remove. This becomes a little bit more difficult. But then boron's electron becomes a little bit easier to remove than beryllium's, and that's because you have an S sublevel that's shielding. So there is actually a situation then where adding an additional proton isn't as effective in pulling towards the nucleus as an additional electron is in shielding. And it has to do with the S sublevel is shielding the 1 electron in the P sublevel more than the protons are actually pulling. So there are 2 situations where it's flipped. It's when you have an S sublevel full. That's when you have your P sublevel half full. Because when you go from nitrogen to oxygen, what are you doing? Nitrogen looks like this, correct?
Oh, okay.
And then when you add an electron for oxygen, you're putting an electron in an orbital that already has an electron in there. And so in this situation, you've got more shielding than you would have protons pulling.
Then why wouldn't fluorine and neon go down? Why do fluorine and neon keep going up if you're also getting orbitals?
Well, it would be, except for now you're adding another energy level and becoming sodium.
Okay, then just for fluorine then, why wouldn't it go down before during fluorine too?
Because I don't know. I guess I'm assuming that at that point, what's happening is the proton being doubly effective in pulling towards overcomes the additional electron that's getting added here. Yeah. There's some breaking point where the initial shielding on that first guy is enough, but then as you progressively go further to the right, the protons overcome it again.
So if you gave us like a question and like which one has a higher ionization energy, like neon or oxygen, you tend to put neon.
Neon or oxygen? You mean nitrogen or oxygen?
You tend to put nitrogen.
Yeah. So think of this is the breaking point, and here at the breaking point. So it takes more energy to remove the second electron, or second group electron than it is from the group 13 electron. And it takes more energy to remove the electron from group 15 than it does from group 16.
Sounds like it's
Yeah. Yeah. And it has to do with the sublevels and how the shielding actually does more because you're giving it you're going to the P sublevel when you jump from 2 to 13, and you're going to the second electron in your P sublevel when you go from 15 to 16.
But that only works if they're at the same energy level.
Yes, absolutely. Because if you're going to a different energy level, that's going to completely change things. You're going to be a lot further away when you're jumping an energy level than just simply going from group 15 to 16 within the same energy level. Okay? All right, that's it. We're done. Hey, wow, we got 13 minutes to do
Yeah,
homework.
homework's already done.
Yeah, but that exception might change.
You're right, I should probably